everyone, welcome to GemChem. Now today's video is on chemical kinetics part 10 video, and here we are going to deal with chain reactions. Now before starting, already 9 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you're new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So first of all, from the word only we can understand that there is something about chain, that is continuous process, right? So in this type of reaction, there is a group of reaction taking place which proceeds through a long series, and the final product which is being formed also generates a reactive species which again undergoes further reaction. So for perfect definition, we can write a group of reactions which proceed by a long series of self-repeating steps. When the final product is formed, active intermediate species is regenerated to carry out the reaction. So this is the definition of chain reaction. Now chain reaction can be of two types, that is stationary, where we can see that there is no branching, non-branching. That is the radical or the highly reactive intermediate which is being formed is only 1 in number, and we can write it as alpha equal to 1. Alpha is the number of highly reactive intermediate. And the second type is non-stationary or branched, where we will get many such species greater than 1. And you have to remember, for this you need to have a better grip on SSA. Now what is SSA? It is steady state approximation, which we had done in our previous video, right? So if you have not watched it, you should watch it and then come to this video. Now we will see stationary reaction in details for this video, and in the next video we will deal with non-stationary or branched chain reaction. Now in stationary reaction, one radical is formed in each propagation step, and these reaction proceeds via a radical process. So first there is a initiation, there is starting. So first step is known as initiation. What happens here is that you have some kind of reactant A. This will produce R dot, which is the highly reactive intermediate, and the rate constant is K1. Next step is propagation. In this, many reaction takes place simultaneously. So this is the next step, which is propagation. In this case, what happens? We have R dot. It can further react with A in presence of a rate constant K2 and produce P plus alpha R dot. Now what is alpha? It is the number of R dot formed, and we know for stationary reaction it is 1, right? So the last step is known as termination, where the reaction can stop. So termination step is also important for the reaction to get ended, right? So in this case, what happens is R dot gets under some reaction and itself gets destructed. So there is a destruction. In some cases, there is inhibition, that is in propagation step there is stoppage of the reaction, which is known as inhibition step. What happens in the inhibition step is that R dot plus product produces A plus R dot, and the effect of net rate gets decreased. Now we need to find out the concentration of R dot, because this R dot is actually our reactive intermediate. So since it is highly reactive intermediate, we are going to apply steady state approximation, as we have seen previously also. So when we apply steady state approximation, we know that d R dot concentration by dt will be equals to 0. And from the equation we can write it as the rate of formation of R dot is K1 A concentration plus alpha K2 R concentration into A minus K2 R concentration A concentration minus K3 R concentration. So let us write it down. Here it will be K1 A concentration for the first reaction. For the second reaction, it will be alpha K2 R dot A concentration minus K2 R dot A concentration minus K3 R dot concentration. From here we can directly write by simplifying that R dot concentration comes to be as K1 A concentration by minus alpha K2 plus K2 in a bracket A concentration plus K3. This can also be written as K1 A concentration by minus K2 alpha minus 1 A concentration plus K3. Now there can be destruction of R dot by two processes. So there are two processes for destruction of R dot. First process is when there is a collision with the wall. Suppose this R dot gets collided with the wall. So it is due to the collision with wall. And the next case can be due to the gas phase. In gas phase it gets destructed. So these are the two reasons, and these destruction processes has their own rate constants, right? So if we consider alpha equal to 0, then the concentration of R dot can be replaced as like this, that is K1 A concentration by Kw plus Kg. So here it is the rate of destruction of radical in chain termination step. This Kw can be actually K3 as we have seen in the previous case in this case. So what we are observing is that when alpha is becoming equal to 1, so the term alpha minus 1 becomes 0 and we are left with K3. So K3 comes to be as Kw plus Kg when there is destruction of R dot. Now we will deal with an example of such a stationary chain reaction. So an example of such a stationary chain reaction is formation of HBr in gas phase. Write down the reaction first. What happens is that hydrogen plus bromine on reaction produces 2 HBr, and this process is a chain reaction. So it will have first step as initiation, right? So when it has first step as initiation, then it will be like Br2 will break down to produce Br dot, which is 2 in number. Next comes our propagation step. Propagation. What happens in this step? This Br radical will react with hydrogen and the rate constant is K2, and one of the hydrogen, which is like this, will give one electron to here and another will keep it to itself. So ultimately what we get is HBr plus H dot. Now we have Br dot as well as H dot. So H dot plus Br2 will again react and we will get HBr plus Br dot. In between we have a step of inhibition. So let us see the step. In inhibition what happens is that H dot plus HBr will react to produce H2 plus Br dot. And the last step of the reaction is termination. So in this termination what happens? The reaction gets stopped. The 2 Br dot will react to form bromine gas. So these are the steps, right? Now we can find out the reactive intermediate. So what is the reactive intermediate? It is Br dot and H dot. And we can apply steady state approximation for them. So let us do that. First we have to find out dHBr by dt. This was a method for finding out the reactive intermediates. So when we try to find this out, we get K2 Br dot hydrogen gas plus K3 hydrogen dot Br2 minus K4 H dot HBr. And from here only we can see that the concentration which is not available to us is that Br dot and H dot. So we will apply steady state approximation for Br dot and H dot, right? First we will have it like this, that is differential of H dot concentration by dt equals to 0. This can be written as K2 Br dot H2 minus K3 H dot Br2 minus K4 H dot HBr. And from here only we can find out the value of H dot concentration. So H dot concentration comes to be as K2 Br dot H2 divided by K3 Br2 concentration plus K4 HBr concentration, right? Now we need to find out for the next intermediate, that is dBr dot dt, which is also equals to 0, and it is equals to 2K1 Br2 minus K2 Br dot hydrogen gas plus K3 hydrogen dot plus K4 hydrogen dot HBr minus 2K5 Br dot. Now we can mark it as this as 1 and the next one this as 2 equation. Okay. Now we will have to add up these two equations in order to get the concentration of Br dot. So we will do 1 plus 2. And on doing so, we will get 2K1 Br2 minus 2K5 Br dot square equal to 0. So our Br dot concentration comes to be as K1 by K5 to the power half Br2 to the power half 3, and we will substitute this value for the concentration of H dot. So let us see, if we substitute the value of Br dot in H dot, we get the ultimate value to be as K2 K1 by K5 to the power half Br2 to the power half hydrogen concentration divided by K3 Br2 concentration plus K4 HBr concentration, right? Now we have obtained the value of H dot as well as Br dot. So we can find out the value of dHBr by dt. This is equals to K2 into K1 by K5 half Br2 to the power half H2 concentration plus K2 K3 K1 by K5 to the power half Br2 3 by 2 concentration H2 divided by K3 Br2 concentration plus K4 HBr concentration, and another term is left for the minus one, and that term is minus K4 K1 by K5 to the power half Br2 half H2 HBr divided by K3 Br2 plus K4 HBr. So this is what comes ultimately when we try to get dHBr dt. This on simplification, and by cutting down all the things present here, we obtain the following term, which is equals to like this: 2K3 H dot Br2. How it came? For this one, we are ignoring these two terms because the terms are becoming more and more big. So we can only take this term. So ultimately what we get is this one. And we can write it down like this: 2K2 K3 K1 by K5 to the power half Br2 3 by 2 H2 concentration by K3 Br2 concentration plus K4 HBr concentration. This can be further relaxed and expanded to obtain 2K2 K1 by K5 to the power half Br2 to the power half hydrogen by 1 plus K4 by K3 HBr by Br2. We have taken the Br2 at denominator. Ultimately, these are all constants. So we can take it as like this. It is equals to K dash Br2 to the power half H2 by 1 plus K dash dash HBr concentration by Br2. So in the initial stage, the concentration of HBr is equal to, most of all, it is equal to 0. Right? HBr concentration is at initial stage equal to 0. So we can write it down that HBr concentration by Br2 concentration is equals to 0. So our dHBr concentration by dt is at 0 concentration can be written as K dash Br2 to the power half H2. We are just removing the denominator. Order is 1.5, that is 3 by 2. From here we can understand. And with respect to bromine, it is half, and with respect to hydrogen, it is 1. Now an important thing which we need to learn in this case is that what is the chain length? New term which is known as chain length. It is actually equals to d product by dt divided by d initiation step by dt. Right? So d product dt, we have already obtained it. So what is that? dp by dt is equals to K dash Br2 to the power half and hydrogen, right? And for d initiation by dt, it is equals to 2K1 Br2, Okay, and these zeros present here represents the initiation at the starting. So what is the chain length which we obtain? Here is chain length equals to K dash dash Br2 to the power half not H2 to the power 1 and not in the downside 2K1 Br2 not. So this is the chain length obtained for our HBr reaction formation, right? So this was the today's topic of stationary reaction. So hope this was helpful. In the next video we are going to deal with non-stationary reaction, and it is very important. Thank you for watching. Do not forget to like, share, subscribe and comment.